Hello, this video is going to be talking through some of the answers to the titration retake assignment. And this is based on commonly missed questions and also some questions that you might see on the AP test, the multiple choice section. So looking here at problem number 1, here's an example of a calculation you need to be able to do without a calculator. So let's talk through this one. So we've got a weak acid. I know it's weak because they give me a Ka value that is less than 1, so it's a weak acid. Usually with strong acids, you're not even given a K value, but if you were, it'd be really large. Okay, so it's a weak acid. I don't know the formula of it. Doesn't matter. I can just consider the dissociation of that weak acid, and if I were to set up an ice chart, I'd say, okay, it's 1 molar, and this is 0, and then it's going to dissociate a little bit, and you end up with this in your K expression. So you'd write out Ka is products over reactants, so it's going to be x squared over 1.0, and that is going to be equal to 3.5 times 10 to the negative 8. And when we do this type of calculation, we're going to solve for x to find our pH, and then take the log of it to find, solve for x to find our H plus concentration, then take the log of it to find our pH. So multiply both sides by 1. Okay, that's easy math. I can do that. And then I'm going to take the square root, and this might seem very intimidating, but recognize you don't need to know the exact value of the square root of this number. You just need to know an approximation. So I'm going to say, I'm just even going to ignore the 3.5. I'm going to say, okay, what's the square root of 10 to the minus 8th? And here's where it helps to know your rules for exponents. So like when I multiply exponents together, I add the exponents, so 10 to the 4 times 10 to the 4 is 10 to the 8th. Therefore, the square root of 10 to the negative 8 is 10 to the negative 4. And that is my H plus concentration. To find the pH, I have to take the negative log of both sides. And here's again where you need to know something about exponents and how logs work. So the log of a value is going to be close to whatever this number right here is. So the pH is going to be around 4. Okay, so if I look over here, oh, here we go. That is option B. So notice I didn't get out my calculator once I did all this. Not really in my head. I was doing scratch work, but you can do it without a calculator. Let's take a look at problem number 2. What's the pH here? So you've got 100 ml of 0.1 molar HCl. So let's look how many moles that is. So it's 0.1 times 0.1. I've got 0.01 moles HCl. Mixed with 50 mLs of 0.1 molar NaOH. So that's 0.05 times 0.1, so that's 0.005 moles NaOH. And the key thing we want to know here is that when you add these together, any H pluses or OH minuses floating around in solution are going to combine to form water. So what that means, my 0.01 moles of HCl, some of that's going to get used up. What I'm going to have left is 0.005 moles of H plus left over. They are combined into a volume of 0.15 liters. So let's think, how do I do this number in my head? So I've got 0.05 divided by 0.15. I can think of this as 5 divided by 150. Okay, so it looks somewhere around like, we're in the hundredth zone here, right? So I'm somewhere around 0.01-ish, right? H plus ions. I don't need to know what it is exactly. Okay, but I need to know that it's around there-ish. So my pH is going to be, or my H plus concentration, I can rewrite that as 1 times 10 to the negative 2. So that means my pH is going to be around in the 1 to 2 range. And it's going to be a little bit higher. And so now I'm curious. Now I'm going to stop and plug this into my calculator. But 5 divided by 150. And you end up with the log of your answer. You get 1.5 is what it is if you plug it in your calculator. But I'm going to do it without a calculator. The key thing is whenever you're in a zone where you've got excess strong acid, you can think about it like we did with the titration curve. So remember when you were titrating a strong acid with a strong base, the pH started low and it just stayed totally low until you hit equivalence, and then boom, and it was like this. So this question is describing this spot right here in the middle where you've reacted half of your use up half of your acid. And you'll remember from the curve, like the pH doesn't really change very much. So the pH at this halfway point is going to be pretty similar to the pH initially. And the pH initially was 0.1 molar H plus. That's 1 times 10 negative 1 H plus concentration. So our pH here was 1. So here in the middle, the pH is still going to be around 1. Okay, so that's another way of looking at problem number 2. Problem number 3, which of the following mixtures form buffers? So in order to have a buffer, you need to have a weak acid and its conjugate base. So a lot of times we use the symbol HA and A minus to look at that, to symbolize that. So if you look here, A is definitely a weak acid and its conjugate base. So if you put that in water, I'll have molecular HNO2, because it's weak, so not very much of it will dissociate. I'm going to have some sodium ions that aren't really going to do anything, and I will have some nitrate ions. So I'll cross out the sodium because they're a spectator. I'm going to have a solution containing HNO2 and NO2 minus. I have a buffer. All right, let's look at B. What's happening in B here is I've got HNO2, and I have some hydroxide. Okay, but if I dump in hydroxide with some acid, it's not actually going to stay hydroxide. It is going to, any hydroxide ions I dump in are going to steal a hydrogen from my acid and form NO2 minus. So and it looks like here I added less hydroxide than I had acid. So it's kind of like I had 100 of these and 50 of these. What happens is all 50 hydroxides get used up, so I don't have any more of those, and I make 50 NO2s, and I used up 50 of these. So what I'm left with, after I mix these two things together, is 50 HNO2s and 50 NO2 minuses. Is that a buffer? Sure, right? I've got a weak acid and its conjugate base. There you go. So B is definitely a buffer. Okay, if you look at what happens here at C, this would be like I had 100 HNO2s and 100 OH minuses. I've got equal amounts of them. So they're going to totally react, and I'm going to be left with pure NO2 minus. So no, this one is not a buffer, because all I'm going to have is the weak base and not the conjugate acid. Let's take a look at B here. Sorry, D. I'm running out of room here. I've got 100. It's like I'm starting with 100 NO2 minuses. I've got 100 sodium ions too, but they're not doing anything. They're a spectator. And I'm going to add 50 H plus ions. Again, I added some chlorides too, but we don't really care about those. They don't do anything. This is the important stuff. Okay, so I'm adding some strong acid to some weak base. The weak base is in excess, so all of my acid gets used up, and what I'm left with is 50 NO2s left over, and then 50 of them have turned into HNO2. So I have a buffer, because I have, the key thing we're looking for here is I've got excess weak base mixed together with a strong acid. Just like over here in part B, I had excess weak acid combined with a strong base. If I look at E is not a buffer, because what happened with E is we added equal amounts of my acid and my weak base, so they totally react, and we're left with a sample that is pure weak acid. So that is not a very good buffer. And then F is not a good buffer because I have nitric acid and sodium nitrate. And yes, they are a conjugate acid-base pair, but they are not a weak conjugate acid-base pair. And it's actually important to realize, why this doesn't work very well. So if you were to picture what this solution looks like, if you mix together HNO3 and NaNO3, HNO3 is a strong acid. That means it totally dissociates into ions. NaNO3 is a soluble ionic compound. It totally dissociates. So in solution, everything's an ion. I don't have any molecule. So what happens if I come along here and add some hydroxides in there? Well, if I add hydroxides, the hydrogen is going to react with the hydroxides. So my pH actually won't change very much. But if I come along and add in some hydrogen, there's nobody in my solution that is going to want to bond with hydrogen, because NO3 has no interest in sticking with H+. It's going to hang out on its own. It's a spectator. So my anion in this solution is not a very good base. It is not a good hydrogen acceptor. So it is not able to act as a buffer because it's not able to remove the hydrogen ions from the solution. Okay. So taking a look at problem number 4, let's keep charging ahead here. We're looking at the pH of pure water and thinking about, what that is. And it might seem very obvious. Oh, well, it's 7. But it turns out this whole pH scale is based upon this reaction right here. So the dissociation of liquid water, I'm going to rewrite it right here. So I've got liquid water dissociating to H+ ions and OH- ions. These are both aqueous. Okay, and it's an equilibrium, so I can set up an ice chart here and consider it. Remember, in equilibria, we ignore pure liquids and solids. So when we write out the K expression for this, it's just H+ times OH-. There's no denominator. And if we were to set up our ice chart, it would look a little bit like this. So we end up with Kw equals x squared. So we just need the value of Kw right here to solve for x. So at 25 degrees Celsius, this is my setup. I end up with x being 1 times 10 to the negative 7. Okay, and then my pH is going to be 7. And that's why we normally think of neutral as being pH 7 is because of this math we just did right here. But it turns out that K values are temperature dependent. They're going to get bigger or smaller depending on that, whether that reaction is endothermic or exothermic. So the pH of pure water is actually going to change at different temperatures. So let's do the same math here with a different K value. So it's still the same setup. So Kw still equals H+ times OH-. So it's x squared equals 3.2 times 10 to the negative 14. And if you stop and you plug this into your calculator, which I'm going to do right now, you end up with 1.8, 1, 2, 3, 4, 5, times to the negative 7th. And if you take the log of it, then you end up with 6.75 as being your pH. So notice my pH is lower, so I have a lower pH. However, my H+ concentration is still equal to my OH- concentration. And then we do that same calculation for C, you will find that it is even lower. Okay, so as the temperature is increasing, it looks as though my K value is getting bigger. Therefore, this number is getting larger and my pH is getting smaller. If I have more hydrogen ions, I'm more acidic, my pH gets smaller. Okay, so take a look down here. Let's analyze what's happening here. So we had our reaction, and K is products over reactants. And as we increased temperature, the K value increased. So that tells me that I am making more products. So as you increase the temperature, the reaction shifts right. And we know that it is going to shift away from that stress that you added. Therefore, the stress must be on the left, meaning heat is acting as a reactant, and the reaction is endothermic. Okay? Looking here at E is getting at, what does it mean to be neutral? And it turns out, what does it mean to be neutral? It doesn't mean that the pH is 7. That's not actually what it means to be neutral. The definition of neutral is that your hydrogen ions are equal to your hydroxide ions. So all of our solutions that we just looked at were neutral, even though their pHs were not all 7. But they all had equal amounts of hydrogen and hydroxide. So water's neutral no matter the temperature, even though you can end up with different pHs.